Right, okay, yes. Good morning, you guys. I hope you guys are doing well. Let's see who's here, who's not here. We have good morning to Nguyen, and good morning to Lila. And we have a number of people online this morning, at least 8. So it'd be 8 to 10, actually. And good morning to Jesus. All right. Okay, let's take a look here at what we're doing. And let's get out go to the browser here. I head out to Math 262. Now it seems as if it'll go to this lower right-hand corner. You guys have something called an online transition. I don't know, whenever we transitioned due to COVID originally, I created a bunch of worksheets and notes because of the transition. So you guys can see this is where I have this online transition. I'll put this in the comment section, I guess. So you guys might want to refer to that because I'll be going through that here too. So I'm going to put here this integration by substitution, which is what we're looking at today here. So I'll put this here for you guys as well. And see what we're going to be using here in this. Let's double check something here. Bless you. All right, so here's kind of the idea. So anyway, let me see what's going on here. Yeah, all righty. All right. This is just kind of the notes to get started here, just so you guys know. Integration by substitution. So here's going to be the link from what we were doing. Like we were working on trigonometric integrals, right? And then now you see this here, and it says, what do you mean, this trigonometric substitution process? Well, any integral that you have that involves this portion here, we could get big, right? We use trigonometric substitution for integrals that involve the following radicals. Generally speaking, you could actually use this technique even if it doesn't have those radicals. You'll see some examples like that. But generally speaking, we use trigonometric substitution for integrals that involves square root of a squared minus x squared, or square root of a squared plus x squared, or even the square root of x squared minus a squared. So we have these kind of radicals here. And it goes back to the idea of a right triangle. So it says we use the tools that are needed in trigonometry. We start with a right triangle with the following fundamental ideas. Remember, you have the adjacent side. So here's my angle theta. I guess I couldn't get theta in at that time for some reason. I don't even remember. But you have the opposite side, adjacent side, and the hypotenuse, right? And that's a right triangle, so there should be a little corner there. And then, of course, we have the Pythagorean theorem based on that right triangle, with the Pythagorean identities based on that triangle as well, believe it or not, or the circle. Circular functions. Okay. And these are my right angle definitions from geometry or even trig, right? The definition of sine, cosine, tangent. And then you have reciprocal identities. But here's kind of the idea. We're going to focus on maybe case 1, something like that, yeah? Case 1. So these types of integrals will involve similar procedures, but use different identities from trig. So we're going to see, for example, a case 1 situation where we have to use our trigonometric substitution here. And I can see, yeah, okay. So let's go over to look at how you can kind of do that. You guys aren't trig. We'll take away that deck of cards. So like for an example, here's what we want to say. You can have an integral maybe that has x cubed divided by the square root of 1 minus x squared. Yeah, 1 minus x squared dx. Okay, so my point I want to make is right in here. I guess we want to look at that. It has a square root here, so this is what I'm saying. It's the case or the type of a squared minus x squared. Okay, so you should see this. And so here's my a squared really, And what they're saying is a is 1. Okay, so we're looking at an integral of this type. So this is what we call a case 1 integral. Okay, it involves the square root of a squared minus x squared. And then you're going to do what's called a trigonometric substitution. So let me go back here and kind of describe some of that for you. Here's what you guys use. You're going to let x be, in general, since this is case 1, right? You're going to let x be a sine theta. And I want you guys to note again. So we have this right triangle here. Here's theta. I guess the legs. Here's C. So for sine, remember, this will be A and this is B, just so you guys know. So the definition of sine theta comes from this right triangle of x over A. So we're going to do it that way. So let me just kind of back off a little bit for that. Okay, so just kind of share with you kind of where this kind of comes from. So just want to recall this right triangle. We're going to use that later, but this is kind of the fundamentals behind this substitution. So we're going to say let x be a sine theta. Now, the second you have x as a sine theta here, for this trigonometric substitution, which you always need is a dx, because this is a substitution. Right? So you're saying, what do you mean substitution? We're going to substitute the x variable with a sine theta. And what that really means, since a is 1, that means that x will be simply sine theta. So once you know what x is, it's sine theta here. What you're going to need is that dx d theta. So you differentiate. So you say, okay, dx d theta, what's the derivative of a sine? Right? That's cosine. But this is a substitution. What I mean by substitution, we want to know what dx is. Okay, you guys okay with that one? So you say, okay, dx, what is dx going to be? Right? Dx is simply going to be cosine theta d theta. So doing a substitution, I'll keep saying that phrase, we have these values here. All right, so I'm going to go back here and share with you guys, where a lot of this comes from now. Right? X is sine theta. So here's going to be our this is going to be our triangle here we're going to use here. But all right, we're going to go back to that. So let me bring this stuff down here. All right, every detail. Copy. We're going to see how this really works. Since x is sine theta here, we're going to substitute that sine theta for x. Right? So, okay, what do you mean substitute? This integral now becomes the integral of sine cubed theta over, we're going to see what happens with that radical. Dx is cosine theta d theta. Okay, so far so good with that substitution. You're saying, what do you mean? This is x, it's sine theta, it's now to the third power. And then we got to focus on the radical here. And you might say, okay, what about the radical portion, right? Right, so here's what's going to happen with this radical. We have 1 minus, we're saying x is sine theta. So this is sine squared theta. Are you guys okay with that? Since x is sine theta, this is our substitution that we use. And then under the radical, what do you guys notice here? Do you guys happen to notice what this is? What is this? Yeah, this is going to be what? Square root of cosine squared theta. This is a Pythagorean identity. Is that right? So if you go back to that worksheet, here's what they're going to say to you. An integral that involves the square root of a squared minus x squared, let that x be a sine theta. And it's really for a right triangle, you'll have really positive angles. And you're going to use this identity. Say, what's this identity? It's 1 minus sine squared theta, which is cosine squared theta. So this is why you'll see in every book under this topic, use that identity. Now, here's the thing about this, right? You guys know this is actually the definition of what? Cosine theta. Okay, you guys okay with that? That's the absolute value of cosine theta. Now, if we go back to how this was defined here, they're saying, what is theta going to be between? Negative pi over 2, right? What do you guys know about the absolute value of cosine theta? See cosine theta, you know what we could do? You could get rid of the what? Absolute value sign. That's going to be strictly what? Cosine theta. Oops, and you can't see that, all right? Here's what I'm saying. That the definition of absolute value of anything is itself if that's what's between the absolute value is positive or 0. So this portion here, what I'm saying is the radical now, and some books will do this, the radical simply becomes cosine theta now. Okay, you guys okay with that? So this is what we call a case 1 situation. And back to this idea here, when we said, okay, in general, you're saying sine theta is going to be what? X over a, or in this case, sine theta is just that x over 1. Remember what the definition of sine is. It's opposite over what? Over hypotenuse, which requires this to be, believe it or not, 1 minus square root of 1 minus x squared by the Pythagorean theorem. So just by using that substitution here with this triangle, we get this nice right triangle relationship here from trigonometry, right? Definition, even geometry, really. But they call this trigonometric substitution. We ended up with an integral. Take a look at this integral. What happens with cosine? It cancels. Is that true? And then what do you end up with, really? Right? The integral of what? Sine cube. So this substitution, using this x is simply sine theta, that one substitution drives this simple, or this actually integral now. It just simply becomes sine cube theta. Okay, you guys okay with that? Now, here's what I typically say at this point. And I say, okay, see what? The previous homework. So the idea is that you did the previous homework and you know how to integrate sine cube. And and that's kind of how that works. If you wait to that weekend before and try to learn how to do trig integrals, and then you say, oh, but I got the trig substitution as well, it's all based on what you've done prior. So does anybody remember when you have the odd power of sine? What is that? How do you do that? Anybody remember this? Odd powers of sine. Yeah, you just factor out a what? Factor out a sine, right? So this is simply sine theta, sine squared theta, d theta, right? And what do you guys use? You're going to let u be what again? I think u is cosine theta, right? So this is the integral of sine theta. And sine squared theta is going to be, yes, it's 1 minus cosine squared theta. But you'll get sine theta now really 1 minus u squared theta. And if u was cosine theta, you guys remember what that was? There of cosine minus sine? So I think it's going to be du over that minus sign here. Right? So this is going to be really the integral of u squared minus 1, ultimately du. So in other words, see homework, because we actually did something like this already. One third u cubed minus u plus c. And you have 1/3, and u, this was u sub, was cosine. Cube theta. Minus cosine theta plus c. Okay, now I'm going to put a box around this, but I'm going to say something here. Okay, I'll let you guys take a look at that. That was u sub at this point, right? This is everything we already did in the past. But you're not done. I'm going to write this down in red. We are not done. So I say we are not what? Done. Right? So why are we not done? Right? This is really the second phase. What was the original integral? It is in terms of x. Is that right? So you have to give your answer in terms of x because this is a substitution question. So you might say, how do I actually give my answer? Right? You guys see where we're at right here? We're saying, how do we go back to x? So here's the big question here. So how do we go back to this x variable? Well, what was x anyway? You guys remember what x was? X was, we say a sine theta. In this case, a is 1. So it's x was sine theta, right? Or we say sine theta was x over 1. Do you remember that triangle that we drew? Right? Remember this triangle that we just drew this? Maybe we should just go back and copy that, right? So x was sine theta, or sine theta was x over 1. So you go back and you say, okay, this is our assumption. You go back to this triangle. So you have to go back to that triangle. Always with these questions, you go back to the triangle. Okay, you guys okay with that? Now you say, well, we got cosine. Well, what's the definition of cosine? Do you guys remember the definition of cosine for a right triangle? Cosine is going to be what again? Adjacent. What's the adjacent side? Square root of 1 minus x squared. Good. Over hypotenuse. What's the hypotenuse? 1. In other words, cosine is just going to be what? Square root of 1 minus x squared, ladies and gentlemen. This is big. This is big. This is... This is what we're going to use here. So cosine is going to go, so in other words, you go, oh, this is cosine cube? Yeah, so this is 1/2. So here's what you can do. You say, final answer, 1/3, 1 minus x squared to the what? 3/2 maybe? You guys okay with that one? Because that's cosine cube minus 1 minus x squared to the 1/2. You guys see where I'm going with this? All right, and then remember this simplification that 3/2, right? If you guys remember from Calculus 1, you actually seen a lot of that kind of thing happening. So in Calculus 1, you might put 1/3, 1 minus x squared. That's the 3/2. That's 1.5. So then you say square root 1 minus x squared minus square root 1 minus x squared plus that c. And there you go, ladies and gentlemen. Here is how you integrate with your first trigonometric substitution, but it is completely based on the prior section. In other words, integrals, you're going to convert every one of these integrals to really a trigonometric integral. That's the short answer. Right? You convert all these integrals to a trigonometric integral, and you are done. And ladies and gentlemen, that's really, there's three cases. That's your first case, you know. Yeah. I have two sides. Okay. All right, let's do another example of case one, okay? This is a case one example, right? It's going to be kind of straightforward. Share with you 4 minus x squared dx here. Okay, so how do you guys know this is a case one, by the way? How would you guys know? You say, okay, even though I've only shown you case one, right? How would you know this is a case one radical? Square root of what? A squared minus x squared. Isn't that right? So you say, let x be what? A sine theta. Okay, so right off the bat, what is a though? Good, so we know a will be 2, because this is 4 is going to be 2 squared, right? So right off the bat, you say, oh, I'm going to let x be 2 what? Sine theta. So here's what you guys want to start with. That's what you're going to substitute. Okay, so this is what's going to be substituted for your x. Now, sometimes if you guys want to know in general, I can show you how to substitute this in general. That your radical will become a squared minus, in general, a squared sine squared theta. Okay, so I'm showing you a slightly different, we're still going to use the identity. It's not going to be a particular case here. But factor out the a squared, and now you're left with 1 minus sine squared theta, right? And that becomes a squared cosine squared theta. Again, Pythagorean identity in general. And then you say, is that going to be a absolute value of cosine? It will be. And then product rule for absolute values. Absolute value of a times the absolute value of what? Cosine theta. That'll be a cosine theta, because again, the angles that you're going to use are going to be, again, going to give you a positive cosine. So here's what some books say. Some books will do this. When they say use this substitution, x is a sine theta, what they'll do is this. They'll say, okay, then replace your radical, the a squared minus x squared form in general, with a what? Cosine theta. So some books will actually just say use this as well. Automatically. Okay, so what that means now for us, you might say, what does that mean for us? Well, the radical is really just going to be what? 2 cosine theta. Okay, so you're going to substitute the radical with this expression as well. This is what some books do. Right, and then you say, well, what's the last thing I need? Well, the last thing I need to substitute is the dx. So once I have x, we know dx will be dx d theta, right? What's the derivative of 2 sine theta? 2 what? Is that 2 cosine theta? Is that true? Do you guys know what I'm saying? You're going back up here, looking back up there. Derivative of sine is cosine, right? Factor that out. So what another book, like I said, there's some books that just lay it all out and say, okay, this is dx going to be a again cosine theta d theta. So, you'll have this relationship given to people as well. So they just go through all of this in general and write down formulas. Here's what I mean. They'll say dx will be a cosine theta d theta. And so they'll say use this. I'll paint it in gold or whatever color that is. X is a sine theta in general. And then they'll say replace your radical with, oops, didn't want to do that. Replace your radical right in here with this. Replace dx with what? With this for your substitutions in general. So they keep the a and they give you all the replacements, the substitution. So in this case, again, I'm doing it, whichever way you choose. Let's actually substitute now. Let's go back to the original integral. So now when you substitute, notice what you do, right? What does the radical get replaced with again? It's right here. 2 what? 2 cosine theta. What does dx get replaced with again? 2 cosine theta d theta. Absolutely. This is your trig substitution. All right? So this is going to be ultimately 4 cosine squared theta d theta. So at that point, I just have to say to students here in general, right, this integral, what I've usually done in the past is just say, see your what? Homework. This is a trigonometric integral. All right, trigonometric integral. So kind of remind people, right? How do you integrate this? If you guys remember, right? You go back to that identity sheet, I guess. All right, let's go back here. Go, calculus worksheets, videos. Where's the trig identity sheet? There we go, trig cheat sheet. Cosine squared, you guys remember what that is? That's going to be what? 1/2 1 plus cosine double theta. Double theta. So 1/2 cosine 1 plus double theta here. All right, so we're going to say, okay. 1/2 1 plus cosine double theta. Is that true? Yes. You didn't, I'm covering that. I guess I can see that. Okay. All right, you guys okay with that? So let's go back and, I don't know, is that red or something? This is the identity. And then pull out that 1/2. That just gives you a 2. 1 plus cosine what? Double theta, right? So you get 2 now. This will be theta plus, this will be a u sub. So if you guys remember, what's the derivative of sine is cosine? So it'll be, and this is u sub b 1/2 what? Sine 2 theta, right? Plus c. So 2 theta plus, distribute this, 2 theta plus sine 2 theta plus c. Now, here, let's just highlight this. Here, you might say, wonderful, you're done, right? But I'm going to remark again, I'm going to say to you, we are not what? We are not done. You say, well, why aren't we done? Because we did a trigonometric substitution where x is going to be here, what was that, 2 sine theta? You guys okay with that? See, we need this answer in terms of the variable x. We can't have it in terms of theta. We need an x variable. All right, so you go, well, how do we get that x variable? Yeah, go back to, well, you're using this relationship. You're right. You're going to use the right triangle. You're going to say, okay, since x is 2 sine theta, right? Doesn't that mean sine theta is x over 2? And go back to your right triangle again. Here's my angle theta. And definition of sine, isn't that opposite? So this is x over hypotenuse 2. Pythagorean theorem will say this will be 4 minus x squared. You're always going to get that radical there. So yeah, ladies and gentlemen, there you go. Here's some knowledge. Now, we got to be careful though. All right, and I remember this is going to be from negative pi over 2. Let's equal theta to positive pi over 2. You know what that actually means, though, ladies and gentlemen? You know what that implies? You know what that means about x over 2? And x over 2, I should say. You know what that means about theta? Right? It means this sign is invertible. Right? Sine is invertible here. So this implies here, using these two pieces of information, really these two, what that means is theta is going to be inverse sine of what? X over 2. Because the function's 1 to 1. You guys know what I mean? It's invertible. So this is how you get a hold of theta, because you go, well, how did I get this theta? This is the theta I'm talking about. Right? So theta is going to be inverse sine of x over 2. Okay, because this is the definition of it. So now you have 2 here. So here's what we're going to say. Oh, that's 2 now. Here's my theta, but it's really inverse sine here, ladies and gentlemen. Right? That inverse sine relationship there. Okay, you guys okay with that idea? And then you might say, well, what happens over here though? We got sine double angle. This is a single angle. All right. Do you guys remember that identity that I said to you always shows up a lot in math and science? The sine of a double angle shows up a lot. And let's go to this sheet here, right? Because this is, you say, this is a double angle, and this is, the triangle is just a single angle. So if I go back here, let me go back to this worksheet, and I'm going to show you one of the most popular identities. There we go. It's a double angle identity. Let's see if you can see it here. All right. What's sine of a double angle? Right? Sine of double theta. What was that? 2 what? Sine theta times cosine theta, ladies and gentlemen. That identity shows up a lot in math and science. Sine of a double angle is 2 sine theta cosine theta. And you guys remember those? Remember when you studied trig and you studied identities and people were like, oh, I don't want to kind of prove these things. You guys know what I mean? They show up. They're in math and science everywhere. So sine double theta is 2 sine theta. It goes right up in here. So you could say, couldn't I have just said from the beginning this is what, 2 sine theta cosine theta? You could, you know, you're using that identity, but let's put it all together here. What are we trying to do here, right? Let's go back so people can understand that. Let me copy this. Right, because you say there's a lot going on there. You use an identity. Right, remember this? Does anybody remember what was sine theta anyway? Do you guys remember? What was sine theta? It was x over 2. Is that right? So what you'll have here is this. Sine theta was x over 2. So we're going to have plus 2 sine theta. This is x over 2 right in here. This 2 is here. I just wrote down sine theta, x over 2. But now what do you need again from the right triangle? Cosine theta. So you go, well, how do I get cosine theta here? What's the definition? Right? Cosine theta is going to be what? Go back to that right triangle. What's cosine theta? I think it's adjacent. What is that? Adjacent. Remember that? Over hypotenuse. Square root of 4 minus x squared over 2. That's your cosine theta. So it goes back to that right triangle. So you say, what do I put down now? So we'll put down what that is. This is cosine. Square root 4 minus x squared. Double check. You sure about that? So you got 2 theta times simply sine 2 theta. So here's the 2. So here's, I thought I've been bringing it all down right here. See this here? This 2 is here. This is sine theta. And then this is going to be what? Cosine theta. So I have to cancel. This was 2 theta. Yeah. That's right. It's an inverse. Yes. That's right. So don't forget, though, we have to simplify, right? Final answer. 2. Inverse sine x over 2 plus, final answer, 1/2 x square root 4 minus x squared plus that c. Okay? There is what you're looking for. So there you go. Okay, so we went from here. This is what I'm going to say. We went from this answer in blue, and you're using the substitution information, the original substitution, to create a right triangle. And then actually, in all honesty, ladies and gentlemen, from that information, you can find theta. You can find sine theta, cosine theta, tangent theta. It's a right triangle. In theory, you can find all 6 what? Trig ratios. Cosecant, secant, tangent, because you have the right triangle here. Where is it? There you go. You have this right triangle. So you're just using all those definitions. And so whatever you even get as an answer in terms of a trig integral gets converted to what? To what you're looking for. Okay, it gets converted here. Anyway, that's the beauty of it. Just looking at this. No, not yet. This. Maybe this. All right, well, let's look at this next situation. Because we say that there's actually what? Let's see. Oh, the inverse sine. The inverse sine happen here? Well, go back to this assumption here. Right? Remember the substitution. This is your original substitution. Since x is 2 sine theta. Right? We say x is 2 sine theta. Now, what that implies then is that sine theta is going to be what? X over 2. So go back again to, what do we call that? Online transition. Let's look at those notes again. What's your theta? Theta is between negative pi over 2, positive pi over 2, which means sine is 1 to 1, which means it's invertible, which means theta, it can be written as the inverse sine of x over 2. So this is what we're saying. You started with a substitution, And you could get, I know you guys can't see that. You started with that substitution, right? X is 2 sine theta. Sine theta is x over 2. It's over the quadrant 1, quadrant 4. That sine is 1 to 1 then, and so that gives you the inverse. And no, we're talking about how to get a hold of theta here. So they're saying, how did you get that theta? That's how we got theta. It's inverse sine x over 2. Now, the 2 theta, the other identity, you said, what about sine 2 theta? Well, the other identity was sine 2 theta is equivalent to 2 sine theta cosine theta. There's no inverse in this one. There's no inverse at all. Yeah, because here you had 2 theta, and you go, the right triangle is only a single angle theta. Yeah, that right triangle. And then you go, okay, what's the second case? So case 2, look at, what do you guys see in case 2 now? Let's see if we can get that in what we're looking at here. Case 2 is a triangle that involves what? Square root of a squared plus x squared. Yeah. Let me see what I have. Trig sub. Order. I have a different order in my notes. Well, okay, so case 2 now. If we look at case 2, or actually, if we start to go back, should we do that? Maybe before I go case 2, I want you guys to notice something here, okay? Do you guys remember the equation of an ellipse? Right? Just to say in general. This is the equation of an ellipse, right? This is kind of an extremely important detail. I know your book has a derivation of it. So I don't want to kind of waste your time. You guys can read that, but I want to kind of go over the idea here for you guys. Remember this is going to be your A minus A. You got the equation of an ellipse. Maybe this is B and minus B. And I might need to adjust. No. Let's adjust it. Right, these are points. Okay, and do you remember in calculus we want to try to find area? Bounded area. Remember this idea from bounded area from calculus 1? There's a way to do this. You can't do this until you take calculus 2. Here's what I'm saying here. There's a classic derivation of how to find bounded area for an ellipse. And here's how you go about it. You know this top curve, right? You're going to try to find the area under this curve here. This is a calculus 1 kind of question. These are my limits for the integral, right? So you say, oh, integral from negative a to what? A. But we need that function y, right? dx. To find this area here, this bounded area under that curve. Remember this approximating rectangle? You go, okay, here's that approximating rectangle. So here's what I want to share with you guys. What you can do, I'm going to find this here. I'm going to find the area from A to 0. And because of symmetry, what do you think the area is going to be because of symmetry? If I find that corner, that quadrant, this is be 4 times the integral from what? 0 to a for some y function, y is f of x, that top function. Okay, so I'm going to get that, I'm going to get the area in black and just multiply it by 4. This is going to be how we get area for a what? Inside of an ellipse. Not area of a circle, but area of an ellipse. Now, the real question is, what is this y? Do you guys know how we get this y function? We need that function. That's y. That's the top curve. Y is f of x. All you got to do is use algebra. Solve for y here. So, I mean, this is the book talks about this, and I'll go into some detail, but I want to kind of mention this, that this is going to be y squared over b squared is 1 minus the x squared over a squared, and y squared will be b squared now 1 minus x squared over a squared. And we're going to have to do some algebra, right? This will be replace 1 with a squared over a squared. Okay, now we can actually subtract, I guess. I get a squared minus x squared over a squared, and I can pull out the a squared. I get b squared over a squared now, and this will now be a squared minus x squared. Now this is the function y squared. What does this mean? This means y is two things. It's plus or minus square root b squared over a squared minus x squared. Okay, and it means two things. Let's do this. Let's do some properties of exponents here. This would be the following. Y is plus or minus b over a square root a squared minus x squared. Okay, so it means two things. Positive, and what's the other one? Negative. Now, there's two curves, there's two answers. This is the case where y is what? Positive. This is the case where y is negative. Okay, there's two functions here because remember, an ellipse is not a function, it's a relation. And you go, well, what did you just find? We just found the top portion here in blue. Okay, so here's the top. This is where y is what? Positive, because it's positive for every x value above, for every, y is positive for values above the x-axis. Is that true? And then y is negative. You say, what is this portion? Well, this is the bottom curve. This is where y is negative, so it's going to be this bottom curve here. So the problem is you can integrate only functions. You can't integrate relations. Only functions. But we can actually cleverly do that and get the area for that blue curve, which is y is positive. The y values are positive for all these points above the x-axis. You guys understand what I'm saying? Here's what I mean. Every point here, the y coordinate is positive. So all the points on that curve are positive. That's why you take the positive portion. Every point down here has a y coordinate that's negative. This is why it's in green. That's why you have that negative sign. So that's the bottom curve. Anyway, here's the idea. What you can now do here is integrate this. This is the y we're talking about. Area under the curve. So you can now do b over a square root a squared minus x squared. And if you pull out the constants, 4b over a, and you integrate from 0 to a, square root a squared minus x squared dx, what I want to remark about to you is simply this. This is a what? Trig substitution integral. The case 1 type. It's the one we were doing earlier, right? That right triangle, square root of a squared minus x squared. It's the same technique where you say, what is x going to be? A sine theta. You know, and then you say, what is dx going to be? Well, that's a what? Cosine theta. What's the radical going to be? A cosine theta. Okay, and so what you would do, really, and the derivation is even in the book. They show you this as an example. But the final answer is going to be pi AB. Okay, so your answer is going to be pi AB after you go through the trig substitution, convert it to a trigonometric integral, integrate it and apply the limits. You get pi AB, ladies and gentlemen. Now, I want to remark about this. What's the difference between a circle and an ellipse? Right? There is a difference. Well, here's kind of something that's fascinating to me. Remember, when you define an ellipse, you always say A is not the same as B, right? You say A is not what? B. Because if A were B, you get a circle. So in your definition of an ellipse, A is not B. Now, if A is B, you get a circle, and you want to know what you get for area? Pi r squared. Is that right? You guys with me on this? This is deep. This is heavy. So here, if A was B, notice this. If we said, no, it's a circle and A is B, you know what you get? Pi a squared. Well, that's like R. A is R. It's going to be your radius. You see what I'm saying here? That's kind of an interesting thing to me when because if I think, what's the area? I can always go back. Oh, yeah. Not pi r squared. It's pi AB because A is not the same as B. And that just blows my mind. See, in other words, you could have not have found that area without the calculus, the tool of calculus. And it's completely analogous to the circle situation. That is just amazing. Pi AB is that. So if you go through if you read the book in that example, I just want to remark that it's a case 1 example. There's an application of finding area, bounded area like we found in calculus 1, and it's pi AB. It's relation to pi r squared. And that's what the deal is here. This is the first time you can find area here. Pi AB. That's kind of a remarkable thing to me. So I kind of did want to do that, kind of mention that for you. Because we have other cases. I guess, let me see what I have here. It's kind of weird. We want to do case 2. Kind of interesting because I have so many. I think I want to do case 2. Is that right? Go in order. Got so many I can do here. Yeah, let's look at case 2, I guess. All right, so we're going to do a case 2 so you guys can see this. Anyway, okay, let's write this down. You might say, what does a case 2 integral look like? We have maybe x cubed square root of, how did I write it? A squared. Okay. All right, whatever. Doesn't matter. 36 plus x squared dx. All right, so if you said, okay, what is that going to be? What does case 2 say? Right? You have an integral that involves the square root of a squared plus x squared. So what does it say we do? X is going to be now what? A tangent theta for, what's the angles? Same thing. Negative pi 2 less than, well, not exactly the same thing. And then what's the identity they say? 1 plus, don't forget, 1 plus tangent squared equals is going to be what? Secant squared theta. So in this case, this is going to be what? 6 squared? You guys okay with that? So A is 6. Now maybe I'm going to do this before we do anything. You see that radical of a squared plus x squared? I'm going to do the general case again. I'm going to plug in for x a tangent theta. So that gives me a squared tangent squared theta. Okay, I'm going to see what this radical becomes. I can factor out the a squared. I get 1 plus tangent squared theta. And then we get square root, I got a squared, 1 plus tangent, this is what they mean by secant squared theta. So that'll be the absolute value of secant theta. Absolute value of A, absolute value of secant theta. I didn't mention this to you guys, but A is always positive, by the way. Okay? So that's why you say 6 squared. You don't say like negative 6 squared. You guys know what I mean? A is positive. So you say, why is that a big deal? Because if I want to get rid of the absolute value sign, the only way I could do that is if A is positive. Now again, secant's going to be positive because it's a reciprocal of cosine. And cosine over that interval is positive. So in other words, we are free to remove these absolute value signs. So the point is, you might want to say this in your notes. A squared plus x squared will always become what? A secant theta. So the radical will always be an a secant theta. Okay, so that's kind of what I want to remark. So some books actually from the start will tell you that. They'll just give you this. You know what they'll do? They'll say x is a tangent theta. So this is the case 2 situation. Some books say, hey, use x is a tangent theta and use derivative of a tangent theta. What's that derivative? Isn't that secant squared theta? D theta. And then they'll say for the radical of a squared plus x squared, use a secant theta. This is your trig substitution information. So some books will do it that way. You know, they give you these 3 things. And that's okay. You know, that's fine too. We just have to try it out. So, all right, let's try this out. Let's copy that. So let's do our substitution. Is that right? What was x in this substitution again? X is 6, what? Tangent theta. Is that true? Okay. So this will be 6 tangent theta to the third power square root. Sorry, no square root. This, and then it's going to be what? Maybe we should color coordinate this, right? Maybe you guys can see this. Here's orange. There's orange. This is what I just did. And then I'm going to say here's green. And I'm going to put down now what? 6 secant theta. I got to replace the radical now. That's the green portion. And then let's maybe use the gold or the brown. Okay. So you guys can see that. Where's the gold and brown substitution? That's going to be 6 secant squared theta d theta. So let's use the right colors here. Okay, you guys with me on that? Do you guys see the substitutions they're saying to impose here on this? And here's the deal. This becomes 6 cubed tangent cube theta times 6 squared secant cube theta d theta. Okay? So I'm going to pull out the constant 6 to the 5th tangent cube theta secant cube theta d theta. So I just pulled out the constants here. So double check, ladies and gentlemen. This is the substitution. This is a case 2 substitution. I think that's 6 cubed. Is that right? Yeah, I put it right here. See this here? This is going to give me a 6 cubed. Is that right? And then I get 6 times 6 gives me a... So here's my 6 cubed. I think here's my 6 squared. So I get that 6 to the 5th. So double check. Am I correct with that stuff? I think it all has an A secant A, right? Double check. I think I'm fine. Now, remember, did you guys study these kind of integrals? What do I mean by that? What do you do when this is an odd number? Tangent is odd. In other words, let me just put that here in blue. Let me circle that. Doesn't like doing ellipses. I'm going to say, what is this called? This is a what? Trigonometric what? Integral. It's trigonometric. So what do you do with those trigonometric integrals? With that's tangent. Don't you have to factor out a secant tangent? Secant tangent. So we know what that leaves you with? Secant squared theta, tangent squared theta. And you're going to have u be what again? U is secant theta, right? So du d theta, we'll say du is secant theta tangent theta. If you guys remember that here. So I'm going to bring down that constant here. 6 to the 5th integral of secant theta tangent theta. Now, so this would be u squared. Is that right? Right in here, isn't that u squared? What do I replace that tangent squared with? Isn't that secant squared minus 1? So this would be u squared minus 1 du over that secant theta tangent theta. You're going to cancel these things out. So you guys remember that kind of, this is again a trigonometric, you got to do the homework on trig integrals if you're going to use trigonometric substitution. And then, what do you have? 6 to the 5th, integrate u to the 4th minus u squared du. 6 to the 5th. 1/5 u to the 5th, 1/3 u cubed. And I'm going to try this. I'm going to distribute 6 to the 5th, u5. I'm going to distribute this, ladies and gentlemen. I like to get rid of that. And we have to remember, what was our u? U is what? Secant? Okay. Secant to the 5th minus 6 to the 5th over 3 secant cube plus c. So in other words, because this is our u was secant, we did we integrated a trig integral using u sub. So to ask you guys at this point now, if you remember this, you might say to me, well, what happens with all of this now? How did you start this original substitution? Remember this? What do we say? X is what here? X is 6 tangent theta. I'm going to bring that down. Remember this portion here? You said, but x is 6 tangent theta. We can't leave the answer in terms of secant theta. Right? We have to have the answer in terms of x. All right, so what does that mean about tangent theta? Tangent theta is going to be x over what? 6. Is that right? So here's my right triangle with theta again. What's the definition of tangent? Is that opposite over adjacent? Is that true? What do you think you're going to get here? 36 plus what? By the Pythagorean theorem. All right, this is by the Pythagorean theorem. So notice what we need. Don't we need a secant? So what's the definition of secant theta here? Isn't that the reciprocal of what? Cosine? So what would you say cosine theta would be? Maybe that's easier. Isn't that going to be what? Adjacent over the hypotenuse? Is that true? So if that's the case, what do you think secant's going to be? Reciprocal. Yeah. 36 plus x squared over what? 6. All right, we're going to have to put this all together. This is what we were looking for, ladies and gentlemen. We're looking for this, if we put the colors, I guess. I don't know what color. Oh, how about in honor of the 80s? Oh, there you go. I mean, Stranger Things is going to come out soon, right? Honor of the 80s. Hot pink. That was really a popular color, ladies and gentlemen, back in the 80s, in case you guys didn't know. You know, it's kind of interesting. It's very interesting. 6 to the 5th over 5, that color. Had a lot of wood grain in the 80s? Yeah, even cars had wood grain. My dad had a Ford Fairmont, and he thought it was so cool because he got the wood grain side panels. you know, you see that now, and you're like, oh my god, it's horrible. I guess you guys have never seen cars with wood grain side panels. I'll never forget it, but it's kind of interesting. Yeah, I remember a lot of things from the 80s. Jesus, I'm going to date myself. Yeah, I was like that kid and those kids in Stranger Things, you know. This is third power. What is that 36 plus x squared over 6? This is now third power, right? Let me double check because I'm thinking now, I'm getting all these 80s memories now. Flooding my head. Yeah, it's kind of interesting. I almost bought a pink guitar just to remember the 80s. It's kind of funny. I think I might get one. I don't know. Yeah, I've been, all the stuff I've been through. Yeah, but I mean, it's an interesting thing. I'm tomorrow. I'm going to be talking to this. Well, you guys know there's a bill called AB 1705. I'll let you guys know, and everybody here at home too. So I invite you guys. I'm in the middle of a crusade, is what I am. I'm on a crusade, ladies and gentlemen. This crusade is about giving students choice and opportunity. Instead of placing students in transfer level math courses, where a lot of students have actually not succeeded, due to this bill, AB 705, and now the follow-up bill that's in play. We're advocating that what they want to do is put every student in the transfer level math and English course, out of high school and existing students. Just say, hey, go in there. The problem is we've seen a lot of data where students haven't been able to succeed with that idea. And so it's created these what's called equity gaps. And so a lot of us are actually against the idea. We want students to actually decide for themselves, give them choice. Let them decide. If they want to enter in a pre-transfer level math course or English, let them do that. Don't just put them in a transfer level where they sink, and then they don't know what to do after that because they can't take anything else. So they just say, hey, keep repeating. Well, after about 3 tries, they kick you out, and then it affects your GPA and financial aid. There's a lot of things they didn't think through. So just on a crusade to give students what we call choice, let them choose. So I'll be meeting with the author of the bill on Friday with a group of people. And I'll be speaking tomorrow at 1 p.m. to our district board who we want to ask them to oppose the bill in its current form, So I'm on a crusade there. So I wrote some stuff up. I'll even send it to you guys. I did it for my statistics class because I'll be teaching statistics, but I want to take them on a field trip. I want to show them, because we're studying probability, I want to show them the data and the information, just kind of blow their minds and show them why we're against this idea, because if it were me coming into school at this time, I wouldn't be here, because I started in geometry, actually, 120. I barely got out of beginning algebra. I started in geometry and then took 125, and I started in pre-transfer level English and math. So if they would have placed me in transfer level English and math, I wouldn't be here. And I know that. I wouldn't have went to school. I would have said, hey, that's crazy. I'm not going to do this. So on a crusade to give students choice and opportunity. That's all. So I'll be speaking to the board in front of the class, and you guys are welcome. I'll send everybody the link. You guys are welcome to take a look and be involved. But I'm actually asking students if they're against this idea and like the idea of giving students choice, just to record, because not everybody can make it at that time to speak to the board. Just record a small video and send it to me of your contribution to being against that, if that's how you feel. It's a small little video. I think that's easy to people do. And now I'm going to put a website together and start this campaign to bring about student awareness of the issue, because they don't even know. And these politicians rely on that. So just causing a little bit of trouble in that way, you know, just giving students choice, because without the choice, without learning how to do things, I wouldn't even be here. That's just the truth. And I wouldn't be buying a hot pink guitar. You guys know what I mean? It's all related to that. And you say, yeah, so I just, like I said, I want students to be able to eat. I'm a guy that says, get the information. It's not where you start, it's where you end. That's the most important thing, is where you end. Get the information you guys need to be successful. You can do it. I know that. You know, if I can do it, anybody can do it. But I had to be a maniac about it. I had to go back and do everything I'm showing you guys. I had to do, even color coding, down to the colors, you know, and doing this stuff, how to approach it. So that's how I see it. But anyway, that's coming up tomorrow. And I sent this out to the district, to different people. So we'll see how this pans out. I'm just trying to get the awareness out. But all right, now you might say, what would I do with this kind of stuff? Let me show you guys something here. Let's do some algebra. This stuff is great and fun. I don't know about you guys. You look at that, you go, oh, horrible. This is 6 to the 5th over 5. And then you know what you're going to see down here? I'm going to pull out a factor of 1 over what? 6 to the 5th. You guys remember, because the denominator has a 6? So we say 36 plus x squared, and that's 5/2, right? Because this is the power of 5 and then the 1/2. Okay. Minus 6 to the 5th over 3, 1 over 6 cubed, 36 plus x squared to the 3/2 plus c. So you can see a cancellation here. And you can actually leave it like this. I'm fine. If you say, I don't want to leave it like that, okay. And this will be 6 squared. So you might see 36 over 3 is what? 12. 36 plus x squared to the 3/2 plus c. And, you know, you can leave it like that. That's fine. Okay? So we're doing some simplification there. And then I might say to you, you might look in back of the book, and you're going to see this answer. And I know I showed the calculus 1 students how to get these answers. This is 2 square root 36 plus x squared. Because sometimes you look in back of the book and you go, oh my God, where did they get all of this, right? You do it that way. So if you guys remember this, remember the technique, right? 5/2 is 2.5, right? That mixed number, 2.5, and then 3/2 is 1.5. And you might say, where did you get the 2 power from? 2 goes here. Where did you get the 1/2 power from? Well, this is where the radical comes in. And then you go, oh, where'd you get this 1 power from? If we go back to orange, right? See this 1 power. And then where'd you get the 1/2 from? Right here. And so if you're looking back at the book, that's where they got it from. So there's a nice, quick, and easy way. If you go, oh my God, how did they get that? Well, convert the improper fraction to a mixed number. That's a nice trick, you know. And then you get exactly what they have in the book. But if you said to me, would I accept the blue version? Yes, I would. That's fine. But as you guys can see, you know, there's some details there. You got to go back to that right triangle to get the trig identities or the trig ratios that you may need. You know, that's kind of. But that's an example of a case 2 integral, you know. Anyway, I'm just trying to see what I have here. Should we do another case 2? See what this case 2 is. Is that a nice case 2 or? You guys want to try another case 2, or you want to take a break? Another case 2? All right. Okay. So I'm just curious, you guys at home there, we got a number. We have at least 10 people at home, usually more than that. I don't know if you guys can see the number. You know, you don't have the number. I have it here. Is it better to be home? Maybe not. You like what? I think, yeah, I mean, people are different, you know, and I have mixed feelings. I'd rather be around people. I don't know. It feels better to be around people. I think people need people. That's my personal feeling. You know, people do need people. Rather be around people, but sometimes it's convenient to be at home. Maybe too. What would bug me is everything at home, like the dogs, the neighbors barking, and everybody around me at home, you know, bugging me. Oh, yeah, I might do the summer course, you know, on campus. I was thinking, is there benefit to be at home? I might do it on campus. Same stuff though. Put it on, record it, you know what I mean, and broadcast it. Record it and broadcast it. But sometimes it's fun at home. I don't know. Anybody here have a nice, quiet location at home? Everything's nice and quiet? Or you guys like me? It's just too noisy. How do we know this is case 2? Square root of 4 plus x squared, right? So what is a going to be? 2. So automatically you say, okay, that means x is 2 what? 2 tangent theta. Dx is, or tangent is secant squared. 2 secant squared theta d theta. And what do we say that radical will be? 4 plus x squared will be 2 what? So I would look it back and I would kind of use this information like I derived for you guys here. Right? 2 secant theta. So some books just, I don't think your book does it this way. I don't think your book gives you the radical too. Some books do, but you know, you derive it, you know, you can derive it once, twice, whatever you need. I'm fine with that. So now this becomes by trig sub no space. Okay, so if we have to color coordinate this to see what we did, there's the x, right? And I guess I'll put the dx first. There's the dx. And we'll put that one in red. Here's the radical. So the trig integral. So I guess it's 2. 2 secant cube over tangent. All right, so we can see this now. You might look at this and you say, okay, so I got the 2 because up here, well, one of the 2's went away. I guess that's the easiest way to say it. So you still have a factor 2. We pull it out, and then you get secant cube over tangent. Now, you're going to look at this and you go, wait a minute. We didn't talk about secant cube kind of over tangent kind of thing. There are some in the trig, I should say in the trig videos, the trig integration videos. You might say to me, what do you do with this? And I'll say, you're going to have to use identities here. Okay, you're going to have to use identities. Now, there's a couple of ways you can do this. You know, I know what I did when I did this earlier. Now, let's try it this way. I'm going to do it this way. I'm going to do it differently. Floating around. What would you guys do in 241 with this kind of question? Do you guys remember? I'm going to try to convert everything to sines and cosines. I'm going to see what I get. How does that sound? Maybe get something nice and easy I can recognize and integrate. I don't know. I know what I did prior. What I did prior, I actually did this. Secant theta, and then I had secant squared theta, what? Plus 1 over what? Tangent theta. I factored out a secant theta. You know, I did that before. And what do I have? Oh, no, that's not what you have. You got this secant squared, right? Secant theta, secant squared theta? That's secant cube. And then what do you think I did here? Yeah, at this point I said, oh, you know what? That's going to be, I know what that is. It's a Pythagorean identity. I had secant theta. And I'm going to replace that with 1 plus what? Tangent square theta. That was all over tangent theta. And then I did the conversion. So I think, you know, really, what I want to try to do, just from the start, okay? I'm going to do it over here. Change colors. What's the definition of secant cube, or secant? That 1 over cosine? And, you know, 1 cubed is going to be 1, by the way. And tangent is sine over what? Cosine. So I kind of want to, I'm going to try to do it a little differently than how I did it before. 1 over cosine cube theta divided by sine theta over what? Cosine theta. Is that right? And then that gives you, really, 1 over cosine cube theta times cosine over what? Sine. And then I get 1 over, what is this? Cosine squared theta, sine theta. And then you say, okay, what can we do if we use reciprocal identities? What does this give you? I think it'll give you what? Secant squared? Secant squared theta, and then what's this? Cosecant theta? So you say, okay, where can we take this? Does anybody know what is secant squared theta? What's that Pythagorean identity? Is it 1 plus tangent squared theta? Cosecant theta, it's a parentheses. So this gives me cosecant what? Cosecant theta plus tangent squared theta cosecant theta, right? And then you might say, can I replace that with sine theta? Let me see. Sine squared theta over cosine squared theta times 1 over what? Sine theta. So I have cosecant theta plus sine theta. Is that true? And that's over what? Cosine squared theta? So cosecant theta, I know I can integrate cosecant theta. And let me say this. Sine theta over cosine theta times 1 over cosine theta. Okay, because you get cosecant theta plus tangent theta secant theta. Our secant theta tangent theta. So here's the point. What color did I lost my color. Blue, 2. There's a 2. So here's my point to you guys. 2 integral cosecant theta plus, I'll call that secant theta tangent theta d theta. Here's what I make the claim, ladies and gentlemen. I'll separate those. Remember I said some of these integrals, you should know? Remember I said you should probably have some of those integrals like memorized. You know what I mean? Like the integral of secant. Oh, I know. What's the integral of secant? Natural log secant plus what? Tangent. Is that right? And then we looked at this one too. Anybody remember this one in your notes? Integral of, I'll tell you what the integral of secant tangent is. Derivative of secant and secant, that's a secant. Is that true? So what's this integral going to be? Do you guys remember this one? What is it? 1/2 natural log. What was it? Cosecant minus cotangent? Double check. One-half natural log absolute value of the cosecant plus cotangent or cosecant minus cotangent? You guys remember? So when I said you guys that time that some of these integrals, they pump up. You guys remember? They pump up. You want to remember those kind of integrals. So 2 times 1/2 gives you just simply natural log. Absolute value cosecant minus cotangent. Okay, plus 2 secant theta. Plus that c. So some of those actually pop up. And then you go, but that's good to have this answer. But ladies and gentlemen, remember what we said to begin with. What was x, by the way? You got to go back to x is what? 2 tangent theta. So you go, oh, x is 2 tangent theta here. So now we have to find what cosecant and cotangent is and secant. So since x is 2 tangent theta, that implies tangent theta will be x over 2. So when you create your right triangle, definition x 2 for square root of 4 plus x squared. Excuse me. And notice, we need a cotangent. I can tell what cotangent is if I know tangent. Cotangent will be what? 2 over x. You say, oh, okay, that'll be 2 over x. And we need cosecant and secant, so I need to get sine and cosine, right? Sine is opposite over hypotenuse. which now means cosecant is hypotenuse over the opposite. So that's going to be a green. Now we need secant. So we need cosine. Cosine is adjacent over hypotenuse, which means secant is hypotenuse over adjacent. And I don't know what color, gold. Right, square root of 4 plus x squared. Right, secant. I think that was over 2. Yeah. Anyway, double check here. Yeah, we put the 2 in, right? And the 2 canceled. Okay, so natural log, here we go. Let's put that in black here. Natural log absolute value. Square root of 4 plus x squared over x. I think minus 2 over x, right? Plus 2. I think that 2 cancels. Yeah. Double check. Square root 4 plus x squared plus c. Double check here. And, you know, sometimes you might even see this natural log absolute value. Square root of 4 plus x squared minus 2 minus natural log plus the square root 4 plus x squared plus c. Now you might say, what happened here? Well, what happened here was they subtracted and put this under the same denominator. And they just used the properties of logs. Log of a quotient is log of a difference, right? Quotient rule. And was there a 2? No, the 2 canceled there, right? Anyway, I think we're fine, but couple of case number 2s here. Anyway. All right, I think we end our break. You guys can get some McDonald's or something. I don't know. Is McDonald's a good option? Not enough time, yeah. I wonder if they can Uber to the classroom. Uber Eats. All right, okay, we're back. And we want to look at case 3 and kick some of these up a little bit, but let's see what case 3 would look like. So if we go back here, let's see what this says here. All right, case number 3. So I'm going to write that down here. Case 3, integrals of the form x squared minus a squared, right? So your substitution is going to be x equals a secant theta. Okay. And again, well, this is going to be for 0. Look at how they define it. 0 less than or equal to theta, which is less than pi over 2. And or pi less than or equal to theta less than 3 pi over 2. So it looks like essentially quadrant 1 and quadrant 3. Okay, now the identity they want us to use will be secant squared theta minus 1 equals tangent squared theta. All right, so I'm just writing this information down. And remember, if they say it this way, remember what that means then. That means that dx will be derivative of secant and secant tangent, right? So it'll be a secant theta tangent theta. And then the radical x squared minus a squared in general, if you use that substitution, that'll be a squared secant squared theta minus a squared secant squared theta minus 1 a squared tangent squared theta, or again the absolute value of a tangent theta, absolute value of a absolute value tangent. And I can see why they do that. Remember, a is always assumed to be positive. Okay, so they're going to say this is what allows you to get rid of the absolute value. So this would be tangent theta, because how they define theta, tangent's positive in quadrant 1. All students take yes. Tangent's positive in quadrant 1. That allows you to get rid of the absolute value. So they define it this way, so your absolute value is there. So again, you might see in some books, square root of x squared minus a squared, they'll say replace that radical with a tangent theta. So you're going to have, I guess, this piece, really this piece and this piece, these three. So square root of x squared minus, all right, we'll try something like that. All right, so actually the simplest example, believe it or not, they have a really good example of this integral. 1 over the square root of an x squared minus 1 dx. A really simple example of case 3. All right, so notice this. If you guys say, okay, you only have that radical, there's no x anywhere, right? So we're going to replace that with, what is a, by the way? Good. So a is 1. So we're going to say the radical gets replaced with x squared minus 1 squared is just going to be tangent theta. And yeah, x is going to be, you said, okay, what was x? Is that a secant theta or 1 secant theta? Okay. X is a secant theta. So then that means our dx, dx d theta, what's the derivative of secant? Secant tangent? Okay. All right, so let's do our substitutions. So 1 over the radical, that's tangent theta. And then what's the dx? Secant theta, tangent theta. And then don't forget that d theta out here. So we'll color coordinate this. This is red, and this will be the gold or brown. There you guys go. Tangent goes away, is that right? So you get the integral of secant. So that's kind of like one of the simplest kind of examples to use that if you guys want to know. Because now, remember what I said before. What do you want to remember? Some of these integrals you want to remember, like secant, integral cosecant, they pop up. So you go, oh, natural log, absolute value, secant theta plus what? Tangent theta plus c. So if you know that one already, you don't have to like prove it all over again. You know that one, secant theta plus tangent theta, right? That's phenomenal. Anyway. All right, now you say, okay, that was all based on the idea that we replaced x. X was secant theta. Okay. So if x is secant theta, or we say, okay, if x is secant theta, here's kind of how I think about it. That means secant theta is x over 1, right? Or it means, what's the reciprocal of secant? Cosine's 1 over x. It doesn't, you don't have to use that relationship. You can say, I already know the definition of secant. But, you know, for me, in all honesty, I kind of just think of the 3, and from the 3, you know, sine, cosine, tangent, I could get secant, cotangent. So definition of cosine is adjacent over hypotenuse. And that means I get the square root of, what is this going to be? Always x squared minus 1. You're going to get this radical there by the Pythagorean theorem. Yeah. Now, the whole purpose of this, since you said, I already know what secant is. It's x. So I already have part of it, right? We need to know what tangent is. So tangent, then, is opposite over what? Over adjacent. So in other words, this is the square root of x squared minus 1. Okay, so final answer. Natural log absolute value of x plus the square root x squared minus 1 plus that c. Yeah. Yeah, pretty straightforward for that one. I don't know if I want to do that one yet. I'll use this one first. Do this one first. Okay, x squared minus 1. Okay. So that one's a pretty good one. We'll look at another example of these here. Integral of square root x squared minus 25 over x dx. All right. So what is that a going to be in this case again? 5, good. And then what is x going to be? Is it a secant theta or tangent theta? Secant theta. Okay. So this means then, derivative of secant is secant tangent. So 5 secant theta, tangent theta, right? D theta. And then the radical, x squared minus 25, what is that? 5. What do we say we replace the radical with? 5 tangent theta here. Okay, there we go. That's 5 tangent theta. So just really quickly, right off the bat, we can get all these kind of ideas there. So don't forget, x goes down here. The radical goes there, and then dx will do gold. And then there'll be 5 secant theta, tangent theta, d theta, right? Double check. Oops, I don't want to do that. 5 secant theta is gone. So it looks like this is going to be the integral. Pull out the 5. Tangent squared theta d theta. So remember, this all comes down to what? If you said, oh, I think we've integrated these before, right? We've integrated tangent squared theta, didn't we? Haven't we had that one? That was, remember the identity, you use what? Secant squared theta minus 1, I think, right? So we have integrated tangent squared. So like I said, a lot of those integrals that you've worked on and that we've seen come back. And so I'm going to, let's try this out. Let's see if we could do this. What's the integral of secant squared, or the antiderivative? I think that's tangent, right? And that'll be minus a theta. Don't forget plus c. So 5 tangent theta minus 5 theta plus c. And you may go back and you go, what was x? Because this is all going to come back to this here, right? Because we have an answer in terms of theta, and that's not good enough. We want the answer in terms of x. All right, so let's paste this here. Right? So remember, this means that secant theta is going to be what? X over 5. Okay, now you guys remember the graph of secant theta? Right? Isn't that the reciprocal of what? Of cosine? All right, so if you think of the graph of cosine, here's what I'm saying. You see how we need a theta? What's the only way we can get a theta here? Secant has to be 1 to 1 for what quadrants? 1 and 3. Is that right? So I got to think, is it 1 to 1? I believe it is. So secant is 1 to 1, so that means theta will be inverse secant of x over 5. Do you guys know what I'm talking about? Be careful. 2 pi over 2, 3 pi over 2. Oops, sorry. That is true. Let me see. Everything I'm doing is true. But however, what do they restrict the domain, if you guys remember? Quadrant 1. Quadrant what? Here. So in other words, this is gone and this is gone. So sure enough, secant's 1 to 1. All right, you guys know what I'm saying? So, okay, we got this portion. So this will be theta. And we just need tangent now. So secant theta is x over 5. So what that means is cosine is 5 over x. Definition of cosine is adjacent over hypotenuse. Remember, this will always be the radical. And the radical here is x squared minus 25. So that will always be, if you use Pythagorean theorem, you'll get this x squared minus 25. Now, remember, what is it that we need? We need tangent, I guess? We need tangent, right? So tangent, ladies and gentlemen, from this is opposite over what? Adjacent. So the square root of x squared minus 25 over 5. And your 5's cancel. So it looks like we're just going to get the radical. Final answer. Here's the radical. X squared minus 25 minus 5 inverse secant x over 5 plus that c. All right. I think I did that one. All right. Okay, here we go. So we're going to kick this up a little bit, ladies and gentlemen. I'm trying to see how we can kick this up. Note. Integrals involving quadratic polynomials. So you might say, what are you talking about, right? So something like this, yeah, what if I try it this way here? All right, we'll do this first one. You guys can see the relationship. X squared plus 2x plus 2, you have dx. I'm going to see how we could do it. Some of these we could do a trig substitution. So here's what I want to remark here. You say integrals revolving quadratic polynomials. Down here, simply this is what they mean. They just mean a quadratic. Okay, so to say quadratic polynomials, it just means, why don't you just say integrals revolving a quadratic? Because that's a quadratic equation. You guys agree with that? X squared plus 2x plus b. What's the definition of a quadratic? Right, anything that looks like this. That's what they're talking about. That's the quadratic they're referring to. So there's a game plan that exists. And the game plan is centered around the following. You want to complete the square for the quadratic. Okay? So you guys remember the process of completing the square here? Okay, guys, remember that complete the square process? You're going to look at the b term, right? You see this b term? The b term is right here. That's the b term. So step 1, for completing the square, take half of b. So 2 over 2 equals what? 1. Okay, step 2. Take that term and square it. And so that means 1 squared is also 1. So this is kind of interesting. I'm going to color that 1. I mean, it's the same answer. Doesn't always come out to be that, but depends on B. So this is completing the square, if you guys remember. So step 3 is, I call that the rewrite step. When I show this in intermediate algebra, I show them what you're going to rewrite the B. Well, it's called the rewrite step. Here's what you guys are going to do, right? Between the bx term and the 2. I'm going to write it this way. This is what I mean. This quadratic is equivalent to. You're going to use the value found in step 2. You're going to add it, and you're going to take it away. It's in purple. Okay? So don't forget, you're going to use that purple term. This is why I changed the color. You always use the value found in step 2, if you guys remember that. I can share with you guys a link if you want to see that. And here's what I want to remark as well. What do you do with these 3 terms here in orange? And what do you do with these last 2 terms in green? Here's what I say. This is completing the square. You factor this orange term, and you simply add the green terms, if you guys remember the complete the square process. So this is a process of completing the square. Now, you don't really factor. Do you guys remember what I'm talking about? What do I mean by that? What goes here in this parentheses is always the value found in step 1. Always. It happens to be the same number, but it's always that number found in step 1. That goes in there. So what I expressed in the 125 class, and I think you do see it in 260, I just tell them, don't really factor, just use the number found in step 1. And then negative 2 plus 1 becomes what? 1. So what I'm saying is that really becomes x plus 1 squared plus 1 in the denominator. Okay, let me go back here. Here's what I'm saying. This is really what you got by completing the square. X plus 1 squared plus 1, and there's a dx. Okay, so simply complete that square. Okay, you guys see what I'm saying right here? This is what you get. So you go, oh, complete the square. So yeah, you do got to remember that process or review it. So you might say now, well, what do I do with this now that we completed the square? How does that really help us? Anybody recognize anything about this integral? Yeah, you could use what? Use u sub. Right? You say, what do you mean? This is my u. And if u is x plus 1, we know du becomes dx. So this integral is going to be the integral of 1 over u squared plus 1 du by u substitution. Now you might say, okay, I recognize this. Does anybody recognize this answer? That's inverse tangent of what? U. Is that true? Okay, so some of those integrals that you studied and work with, they're going to come back. That's why you want to, it's not like they go away. It's not like you finish that section and you go, okay, I'm never going to remember this integral. No, it's back here. But u is going to be what? X plus 1. So you get the inverse tangent of x plus 1 plus c here. So, okay, we got a pretty good situation here. Now, the reason they give you this one, I'm going to give you a note here, because what if you had the square root of that? X squared, what was this? X squared plus 2x plus 2 now. So you go, oh, what if they gave me this, x squared plus 2x plus 2? again, notice you have a what? A quadratic. Yeah, exactly. So this is the whole idea here. Notice you have a quadratic here. You might say, well, what do I do with that quadratic? Well, it's the same exact process that this integral, using the complete the square, you got x plus 1 squared plus 1, right? And now you let u be x plus 1, where du is dx. I get the square root of u squared plus 1 du. And then I'm going to ask you guys this question here. What do you think you would do now? What do you use here? What case? This is a trig substitution question, right? What case is that one? Huh? Case 1, 2, or 3? I'm looking at it right now. It's right in front of me. Case 2. Yes, it's a case 2 scenario. Yes, you would use case 2. Anyway, exactly. Case 2. So for case number 2, if you remember, what do you let u become for case 2? Right? This is a trig sub question now. U is going to be a. What's a here? Isn't u going to be just tangent theta? Is that what case 2 was? I don't remember. Oh, it's tangent theta. And then what was the radical going to be? Replace the radical. It's going to be a what? Is the radical just secant theta? I think so. And then what is du d theta? Ain't that secant squared theta? D theta. So by the u substitution here, we get 1 over the radical, that's secant theta, du, is that secant squared theta d theta? Double check. Double check. Did we make a mistake? What does case 2 say? Ah, we made a mistake. What is u? No, did we make a mistake? Double check, because we're out of time. So, okay, u is tangent. What's du? Secant squared. Double check. Is the radical going to be just... Is the radical okay? You sure? What's the radical in case 2? I'm going to have to deduce it all over again for case 2? I used to. Here's case 3. Go back to case 2. Where's our case 2? It's going to be 1 secant theta, so it looks like it's secant theta. Is that true? Okay, so we got secant theta, and then we have... So double check. Tell me, is this true? Is this just going to be the integral of secant theta? Double check. If it's true and everything's fine... Thank you, Lela. You're right. If it's true, everything's fine, then remember I said some of these integrals show up over and over again? So those are kind of ones you want to double check. So double check the work, ladies and gentlemen, here. We'll do a few more next time. Um, yeah, where's my notes on this one? Anyway. Oh, here I am. I don't know. Double check, ladies and gentlemen. And what you're going to do here is this. I put your homework online to try some of these out, 5 to 29 odd. We'll do a few more next time, some quadratics. And put your name in the comments section, and we'll see you guys later, okay? A few more quadratic intervals.